Okay, we're continuing our work in Unit 6. In Lesson 1, you were sort of reviewing the development of the law of sines and the law of cosines from trig. Today I'm going to start with an introduction to vectors. And just I've pasted definitions here. So what is a scalar? A scalar is a quantity that has a magnitude but no direction. And a vector has both magnitude and direction. So the first thing we're going to think about is a kind of a bit of a matching. Got about 9 words on the bottom, and then what you're going to do is you're going to decide which are scalar and which of the quantities are vectors, and then might be best too if they're sort of measuring similar things, but one is scalar and one is vector. And as always, you're in control of the timing. You can move forward whenever you wish. Pause the video if you want more time to think. I'm just going to head on and I'm going to move forward. So we could see that distance and displacement are our scalar and vector quantities. Just going to turn that sound down. Are our scalar and vector quantities. Speed is scalar, velocity is vector. Mass is scalar, weight is dependent upon the planet and the force of gravity, so it is definitely a vector. Force is a vector. Temperature is a scalar, but I put them on different rows because they're not measuring the same thing. And now area, we would think would be scalar, but you'll see in Unit 7 when we're going to look at cross product, we'll consider something that's called a directed area. So if we could consider it a directed area, then it's possible we could view it as a vector. So I'm going to put that one in the middle because that one's a bit ambiguous. All right, so on the next slide, we're going to talk about how to describe vectors. Now, the description I'm going to do now in this particular unit, I just want to change that, different color, different thickness. We're going to be doing geometric vectors in Unit 6, and we're going to move on to algebraic vectors in, well, no, we'll do algebraic vectors later in this particular unit. And then Unit 7 will be applications of them. So geometrically, it's going to be a directed line segment. I'm going to have to give you a magnitude. There's the magnitude. And then I'm going to have to give you a direction. And I'm going to physically have to draw it, or I'm going to have to state a direction. So in this particular case, I've drawn the vector. And its length is being... What do I have its length at right now? Its length is at 8. So this is kind of like a scale diagram where every centimeter would represent 3 kilometers per hour. Naming vectors. So how do we name vectors? 2 ways we can name them. We have a tail. The tail is at A. The tip is at B. So we can name this vector, vector A, B. And I am going to show you the proper way to do it, but I couldn't do it. I didn't have a symbol in here for this. It's really a half arrow like that. But in the notes, I didn't want to have to draw that every single time. So there isn't like a half arrow in here. So every time you see this arrow, it is really meant to be this half arrow symbol like that. So 2 ways to name it. 1, uppercase letters. Points are always represented with uppercase letters. This vector is showing the direction from point A to point B. It's also possible to use a single lowercase letter to represent a vector as well. So this is either vector AB or vector U. And vector BA is traveling in the opposite direction. So we could label it as negative vector U or BA. I think that's all I need to cover on that particular slide. Let's move on to the next one. Vectors are determined by their length and direction. The length is called the magnitude of the vector, and it has special symbolism. So if we use these vertical bars, which you're familiar with for absolute value, in the linear algebra or in vectors, they actually stand for magnitude. So this would be the magnitude of, and then inside here we'd have to have a vector name. So the magnitude of vector A, the magnitude of vector B. Magnitudes are always positive. And now we need a direction. So we figured out the magnitude. It does have a length. Now it needs a direction. So 2 ways we can give direction. One would be using quadrant bearings, reference from our primary directions, north, south, west, and east. And so let's say for this particular angle here, we could say we are north 60 degrees toward the west. I could also say I am west 30 degrees toward the north. And I suppose I should put that in blue so I know I'm still referencing this angle here. This one over here could be referenced the way I have here as east 30 degrees toward the south. Or alternately, if I come from this way, I could say this is south 60 degrees toward the east. So in terms of quadrant bearings, there's really two ways to represent every angle you could possibly draw. The other way to do it is bearings. Now this is a bit different from math, because in math, when we think about angles, we start here from the positive x-axis and we head around in a counterclockwise manner. In bearings, you start from what would be considered north, right? And that, of course, would be the positive y-axis. And then you go around in a clockwise manner. So a bearing of 50 degrees would look like this. Start at north. We're going to head this way. And 50 degrees would be right there. So we've started at north, and we've come on a bearing of 50 degrees in a clockwise manner. If our bearing was 225 degrees, then again, we're going to start at north. If we travel this far, we're 180. We'd need to go another 45. So we would be here, so that this angle would be 45. And then our bearing here would be from the north to here. That's 225 degrees. Notice how we're rotating in a clockwise manner. More definition-y type stuff. Equal and opposite vectors. So equal vectors will have the same magnitude and the same direction. So AB, vector AB is equal to vector CD, and notice the magnitude of vector AB equals the magnitude of vector CD. Now this is sufficient. If we just say that vector AB is the same as vector CD, i.e. they're equal vectors, then that implies their magnitudes are equal. If the magnitude of two vectors were equal to each other, that does not mean that this vector is equal to this vector. That's not necessarily true, and I'll show you what I mean by that. I'm going to make a copy of this. And then I'm going to flip it. Left, right. Okay, so now this vector here has the same magnitude of vector AB and vector CD, but definitely not the same vectors. So again, I'm going to repeat it. It's important, it bears repeating one more time. If we have vector AB equals vector CD, that says it all. That's enough to say that they have the same direction and they have the same magnitude, so it would be redundant to write that. If I have two vectors that have the same magnitude, that doesn't mean they're equal. So if two vectors are equal to each other, they definitely have the same magnitude. If two vectors have the same magnitude, it doesn't mean that they are equal to each other. Opposite vectors have the same magnitude, but they point in opposite directions. So note vector AB is the opposite vector of CD. So I can say that the way I've written it here is that AB is equal to negative CD, but I could also say that negative AB is equal to CD. So these two vectors are opposite, and again, if two vectors are opposite, it automatically implies that their magnitudes are the same. So two opposite vectors, their magnitudes are equal. This right now will tell us that two vectors have opposite directions. All right, so that covers the definition of equal and opposite vectors. Let's move forward. Why is direction important? So let's think about this. So let's say a person has left Hamilton, they're traveling at 60 kilometers per hour. After 2 hours, where are they on this particular map? Is direction important? Do I know where they are without knowing the direction that they traveled in? And again, you can be in control of the timing. I'm just going to move forward. We would know how far they did travel, and presuming, of course, that they were traveling in a straight line, they would get the furthest distance away. But if they weren't traveling in a straight line, now we are in the unit on vectors, so then we will not be changing direction. So if they traveled on a straight line, what I've done is I've constructed a circle so that the radius of this circle is 120. So the radius is 120 kilometers. So where are they? They're somewhere within inside this circle. I have no idea what direction they were traveling in. And because this is a unit on vectors, let's presume that they weren't changing direction. If they were, I mean, they could still be in Hamilton, right? Because they just kept changing direction within Hamilton. So direction is important if I want to know the final position. And of course, I would also have to know how many times you had changed direction in order to determine the final position. All right, so we've covered all of our key concepts. We've talked about what a vector is. It needs to have direction and it needs to have a magnitude. We've talked about how to define directions. We could use quadrant bearings, we could use bearings. And we talked about the definition of equal and opposite vectors. Those are our main concepts for today or for the day. And now what we're going to do is we're going to look at some example problems. So in this particular example, we know that AB is a vector. It has its tail at -4, 2. It has its tip at -5, 11. What we're going to try to do is calculate the magnitude of AB. And of course, remember, there was no symbol within Smart Notebook, this half arrow sort of thing. So rather than having to draw it each time, I just went with this arrow, which actually is one you would use to represent an array. And it's not an array, but a ray. So a line segment has 2 endpoints. An array has 1 endpoint and continues on forever in one direction, and a line continues on forever in both directions. So the symbol I'm using here is actually for a ray, because unfortunately Smart Notebook doesn't have this half arrow symbol for a vector. So the first thing I think you should do is draw a diagram. Sort of create a rough axes, plot roughly where those points are, and then draw the vector. Again, you can be in control of the timing. I'm just going to move forward. So here's my rough diagram, and the vector has its tail there and its tip here. So really I should draw the tip in. So let's just draw that. So that's the vector we're looking at right there. So now what you're going to do is you're going to be able to calculate the magnitude of this, and that won't be too bad because we do know this is a right angle. So this is just a Pythagorean theorem. You can figure out how long that is. That's delta y. And you can figure out how long this is. This is also delta x. Once again, you can be in control of the timing. I'm just going to move forward. So we're looking at delta y and delta x. So subtracting the x coordinates, delta x all squared would be -1 take away -4, or -5 take away -4 all squared. And delta y, the corresponding delta y, would be 11 minus 2 all squared. That's going to give me, moving on to the next slide, -1, -5 take away -4 is -1. I need to square that whole value. 11 minus 2 is 9. I need to square that. On the next slide, that's going to give me 1 plus 81, and 1 plus 81 is the square root of 82. And then we have to think about whether or not we can reduce this, and we're going to get 41 times 2. Both of these are prime numbers. Neither of them are perfect squares, so we cannot simplify this any further. All right, the next thing you're going to need to do is describe its location. So the first thing I think you need to do is mark on the angle. This is the angle we are interested in, and what trig ratio is going to help us find that. And of course, bear in mind, we've determined how long these are. This is 9, and we've determined, of course, that this is 1. So moving forward, we're going to use a tangent now, because we've determined that this was the angle I am interested in is right there, theta, right now, because the vector goes this way. So you need to find the angle between the tip and some other reference line. In this particular case, I'm using the reference line to be north, and I'm probably going to use bearings, so I'm going to have to come around like that. It's also possible that we could describe this using quadrant bearings. And the two measures we have are the opposite, that's opposite, and the adjacent side, and that would be a tangent ratio. So I'm going to need to use a tangent ratio. And again, there's the angle we're interested in. We've already discussed this is 9. And that is 1. All right, so we were talking about tangent, and we did say that tangent should be opposite over adjacent. Initially, I had that as 9/1. That's not correct because the angle is right here. The opposite side is 1. The adjacent side is 9. So we now have the tangent of theta should be 1/9, and we're now going to solve that. So the first thing we should do is do an inverse tan. So we're going to get an inverse tan of 1/9. Plug that into our calculator, and rather than work in radians, because we are given bearings and bearings are measured in degrees rather than radians, I'll make sure my calculator is in radian mode, and the inverse tan of 1/9 I'm going to round to the nearest tenth, and I'm going to get theta is equal to 6.3 degrees. So this angle is 6.3 degrees. And now in order to find bearings, bearing would be swinging all the way around like that. So moving forward on the next slide, show that swing around like that. Then what I'm going to have to do is, I know this little bit here is 6.3. I'm going to have to subtract that from 360 to find the measure of this purple angle right there. So 360 minus 6.3 is 357.3. So I'm on a bearing, and I'm going to draw that vector in. I'm on a bearing of 353.7 degrees. Or alternately, if I want to use quadrant bearings, I can say I'm north 6.3 degrees to the west. So we'll move forward to the next slide. And there we have it. Vector AB is on a bearing of 353.7 degrees, or it's north, heading 6.3 degrees toward the west. And the length was the square root of 82. That was example 1. And now we will have a second example that we're going to take a look at. So the previous example was looking at magnitudes and directions, and this next example is going to review the other concepts we discussed were equal and opposite vectors. So we now have rhombus, and given that it's a rhombus, remember what that means, that all of the sides are equal in length because it's a rhombus. So name vectors that are equal to AB and vectors that are equal to DA. Remember, AB runs like that. Now all of these sides, so all of the vectors, BC, CB, CD, DC, AD, DA, AB, and BA, all of those vectors have the same magnitude. But remember, in order to be equal, we also have to have the same direction. So you're going to need to find another vector that has the same direction as AB. And again, you can be in control of the timing. I'm just going to move forward. And the vector that is moving in the same direction as AB, which is this way, would be this vector here, DC. So AB is equal to the vector DC, or DC is equal to the vector AB. It's also possible now that we could say the opposite of CD. So the opposite of CD would be DC, and we could also note the opposite of BA would also give us AB. So it looked like initially there's just one thing we could write, the vector equal to AB is DC, but noting that we could then flip that to vector CD and then note we're the opposite of CD, and we're also equal to the opposite of ourself. So AB is equal to the opposite, actually not the opposite of ourself, but the opposite of our opposite is us. So vector AB is equal to the opposite of its opposite. All right, now let's see if you can run through that for this particular vector. So there is DA, and see if you can find all three possibilities. Again, you can be in control of the timing. I'm just going to move forward. So the first thing we can say is that vector DA, which is that vector right there, is going to be equal to vector CB. Those two vectors have the same magnitude. They are parallel to each other. I didn't mention that when I talked about these two. How do I know they have the same direction? It's a rhombus. And if they are rhombus, opposite sides are parallel. If they're parallel, they have the same direction. That is why we know that AB and DC had the same direction, because they were parallel. So now we'll play the opposite games. We now can be the opposite of BC. BC is the opposite of CB. If we then take the opposite of that, we're back to where we started from. We can now write AD, because AD is the opposite of DA, but if we put the minus in front, we are the opposite of the opposite, and that brings us back to where we started from. And now this one is vectors that are opposite CD. So again, now we're going to start with the opposite. So the vector that is opposite CD, which is this vector going this way, needs to be parallel to it, but it needs to be heading in this direction. And of course, that would be vector. Well, AB, I started by noting that CD is the opposite of DC, and then noting what DC would be. So CD is heading this way, and as I mentioned, we're after vectors that are going this way. So its opposite would be DC, and vectors that are equal to DC would be AB. So AB is the opposite vector of CD, and then we could also play the game the opposite of its opposite, and that is going to give us negative BA. And the last one we want to look at is vector EB. So there is vector EB, and I'm not sure what you remember about the properties of rhombuses, but the diagonals of a rhombus do bisect each other. So this line segment will be equal to that. AE is equal to EC, and EB would be equal to ED. Those would be equal because I do know the diagonals of a rhombus bisect each other. So having said that, we just need to be heading in the opposite direction of EB. So EB is going this way. The opposite direction would be BE. So I'm looking for vectors that are equal to BE. So EB, the opposite vector is BE, and the vector that is equal to BE would be this one here, which is ED. So that's equal to vector ED, but then we can play the same game we played up here. It could be the opposite of the opposite. The opposite of ED is DE, so the opposite of DE is also ED, and that takes us to there. All right, so that brings us to the end of this lesson. Bit of a shorter one. What were the key concepts that we were covering today? We're talking about what vectors were. Vectors have to have a direction and a magnitude. We talked about how you can name vectors. We talked about the symbols, these which look like an absolute value, do represent the magnitude of a vector. And in terms of measuring directions, we could use quadrant bearings or we could use bearings. And then we gave the definition of equal and opposite vectors. So that brings us to the end of lesson 2. If you made it to the end, thank you for watching. Stay tuned for lesson 3. And as always, take care.